Welcome back. In the last video, we asked the question, is there a better way to find a number in a sorted list? And just for this example, let's add an extra number to our list. That's better. Let's say I was looking for 34, and I knew that my list, let's say array, was sorted. What's a better way to go about it instead of checking every single item one by one from left to right? Well, we can use something called binary search. Because we know the list is sorted, we can discard half the items instead of one at a time. Let me show you. We can start in the middle of the list and say, is 9 higher or lower than 34? Well, 34 is higher than 9, so let's discard everything to the left of it. And then we go to the middle index again. In this case, there's no technically a medium, so let's just choose 12. Go to the left of the medium. Is 12 higher or lower than 34? Well, it's definitely lower, so let's remove everything to the left of it. And then let's find the middle index. And, oh, we just found 34. Instead of going through the item one by one, we did that in 3 operations. And this looks familiar, right? And it's something we learned about when we talked about trees, specifically binary search trees. Because if our data is sorted, we can do better than O of n, or linear time. Because this sorted list might remind you of something. We're essentially creating a binary search tree. Unlike linear search, we can discard half the items instead of one at a time. And you might be thinking, well, that's ridiculous, Andre, because in order for us to even search this, we have to sort the list first, and that takes computational power, right? But storing data in a data structure like a tree instead of a linear data structure like an array is actually more efficient. And this is something we've already discussed with tree data structures. As we insert items, if we sort them, it actually gives us better performance than adding it to an unsorted list that we have to search through one day. And because in a tree, where we make a decision, should we go left or right? Should we go left or right? And we discard half the items every step. This should trigger something in your brain that's saying, oh, this is a divide and conquer approach, which gives us a log of n time. Because log of n comes from the fact that we're not visiting all nodes. Each step down the tree, we're eliminating nodes. So this is the deal with binary search. You split a list of a sorted item and decide from there whether item you're looking for is in the left or the right of the list. And because the list is sorted, you can make that decision very easily by just comparing things. And we just keep going until we find what we want. In this case, number 34. We make 1, 2, 3 decisions. And this makes sense because if you're a teacher that's looking at a stack of essays and papers by students, if that stack of paper is not organized, then you have to go through it one by one to find, let's say, Timmy. But if the stack of paper is sorted alphabetically, then you can find Timmy by dividing the papers half each time until you get to Timmy, just like a phone book. We start with n elements. Then when we step down, we have n divided by 2 elements remaining. And as we step down, we have n divided by 4 elements remaining. And we keep going until we find our element. And in the sorting section, we learned that merge sort and quick sort are doing the same thing. And we also learned how to actually search through this tree in our data structure section, right? With linear search, we had for loops. With a binary search tree like this one, well, we had our lookup method where we checked the left node and the right node and divided up the list using a while loop in half each time. So we know how to do linear search and binary search. We know that binary search is going to be log of n, time complexity, versus linear search, which is O of n. But what are these two? Well, up until this point, we've talked about when we're searching for an item, where we know that 34 exists, our list is sorted in a binary search tree, and we know where to go, left or right. But sometimes we have to do something called traversals. And traversal simply means, well, going from node to node, either finding a specific thing or making sure that you touch every single node. Perhaps we want to add a color attribute to each node here. Perhaps we want to update these numbers and multiply them by 2. In that case, we have to visit every single node. How do we do that? Let's find out in the next video.
Yeah.